Okay, sorry about that. So basically, Qdrant is one of the services available out there. This is an open source vector search engine that you can integrate with your applications using some popular interfaces such as HTTP or gRPC, but there are multiple SDKs available. And what's more, you can combine semantic search with full text filters or geo-coordinate filters, actually different kind of filters depending on the data you have. So it's not only about similarity, but also about putting some additional constraints. And our mission is to make vector search affordable by introducing several optimizations that I'm going to briefly speak about today. So this is the most basic structure in Qdrant. I'm not sure how many of you are already familiar with vector databases, but they have different ideas of how to implement certain things. In our case, every single point in a collection consists of ID, which is a UUID like string or integer, an optional payload, which is an arbitrary JSON object. So you can put some nested structures if you prefer to, and vector, which is the most important component, just because this is all about semantic search. And those vectors are brought by our by our users. We do not integrate embedding models into the application. Probably you know best how to create the embeddings for your own. So this is just a effective semantic search layer that we provide you. And there are two processes involved in semantic search. The first one, an offline process, is done to create a database or a collection of points that you wanna be able to search over. So there is a neural encoder that we use to encode all our documents and create embeddings out of them. And those embeddings, along with the data used to create them, is stored in Qdrant. So this is an online process, and the bottleneck of all the processing, creating the embeddings, takes quite a lot of time. And there is also another online process this time. So it's all about querying the database. So we use the same neural encoder. This is a by-encoder architecture. So here we use the same model, create an embedding, and then use this query embedding to find the most relevant items using some sort of similarity measure. Usually it is cosine similarity. And our database performs this approximation of K and N to provide us with possibly the most relevant documents available out there. The second issue, vector search is not all we need. This is usually combined with some additional criteria. Let's say you have multiple users and you don't want to mix the data coming from multiple users. That might be like different organizations, and definitely you shouldn't be mixing their data to provide a response. That's exactly the same problem like we solve with some other systems. If you have like a SQL database, you are usually providing the results coming from a specific account, not all the rows from a specific table. And that's basically a challenge when it comes to semantic search, because we were struggling a lot in terms of combining those two modes of search effectively. Imagine you are looking for a specific piece of cloth and you want to be able to find it using reverse image search, so similarly to what you do with Google Lens, but you also want to put some additional constraints. Maybe you have you want a specific manufacturer or a specific fabric or a color which is that you like. So those are additional filters that are not that well captured by the vectors. Definitely, the price may change over time, and it won't be put as a part of the vector representations. That's for sure. So if you want to combine it, we have it already integrated. And the good thing is that there used to be like two strategies. There was pre-filtering and post-filtering, both having their own disadvantages. But we were able to integrate it directly into the semantic search phase. So you can actually traverse the HNSW graph effectively with those constraints being applied in the same time. And the most important challenge of vector search are the memory requirements. Vectors tend to use lots of memory, and usually we need to choose two out of those three features. So we either want to have a fast and accurate semantic search system, or fast and with low RAM requirements, or low RAM requirements and accurate system. And it's impossible to actually achieve all of that at the same time. So another issue is that in order to perform vector search effectively, we need some random access to our data. We never know what will be the closest entries in the database, so we are usually just picking some random items from a collection. That's why our memory requirements are that high, because we usually store all of that in RAM just to allow this random access to be as fast as possible. And this memory consumption comes directly from the fact how we store our vectors. Those are usually from a few hundreds of dimensions up to a few thousand. So those are the most typical dimensionalities for the most popular vectors. For example, OpenAI produces vectors with over 1,500 dimensions. And if each of them requires just every single dimension requires like 4 bytes to keep the data, at least when you use float 32. That means that we need 6 kilobytes just to store a single vector. And the typical setup consists of at least 1 million or even a few millions. But even if we limit ourselves to 1 million of documents, that means we need 6 gigabytes of memory just to handle the vectors. But there might be some payloads attached to the vectors and some additional data structures that we build. So it's just a lower limit for this kind of estimate. So if you are really building vector search applications, you will be probably dealing with more than a few millions. So that has to be optimized unless you are able to afford a few terabytes of RAM attached to a single machine. I'm actually not really sure if this is right now possible to have 6 terabytes of RAM on a single machine. So definitely that requires some tweaks to be able to handle that efficiently. So there are various optimizations available out there that I'm gonna briefly describe. Another issue is that actually mentioned that a moment ago, but basically we cannot afford to put more and more RAM to a single machine. That has to be split across a number of machines working as a cluster. It also cannot handle like an unlimited number of requests at the same time. So it's always better to spread it across several machines. So the first optimization, the most obvious one, is to just allow to store the data on disk. And this is okay as long as you don't care much about the performance. I mean, if you can agree to have higher latency, it's all fine, because all the components of Qdrant collections might be stored on disk. Vectors, payloads, and the HNSW graph. And we were able to fit 1 million vectors to a machine with less than 200 megabytes of RAM, which is okay, but the latency is unacceptable in most of the cases. Unless you have like a few queries every single day, you probably cannot like store everything on this, but still you can experiment and combine different approaches. Maybe putting your vectors into this does not impact that much the performance of your solution, and you can accept it because the memory requirements and price is way lower. Also, the huge advantage of using HNSW is the fact that it can be effectively scaled to multiple machines, because it might be easily divided into multiple segments, and those segments might be just running on different machines. It's more like map-reduce approach. So you can send the same query to different machines. They will search over the segments of the data. That will be like the map phase, and then the reduce is to choose the closest points from all those subqueries that we have sent before. So that might be easily replicated and distributed across a whole set of servers, acting effectively as a cluster. So this is pretty good choice when it comes to vector databases, and that's also why like majority of players here use that specific algorithm. And another scenario is when we cannot sacrifice the performance. We expect the system to be responding as fast as possible, but we can agree to lower precision of search. If you don't work with like some restricted domains, and you can agree that your users sometimes won't get most relevant document available for a specific query, that should be okay. And here, there are lots of optimizations that we can do directly on a vector level. For example, by default, we are using flow32 to store the vectors. But if we can reduce the memory requirements of a single dimension and use an integer instead with just a single byte, and surely reduce the possible number of vectors that we can represent, that means that we can reduce the memory requirement by up to 4 times easily and still get decent results just by doing that. So that's one of the first optimizations that we have introduced in order to achieve billion scale, even on a budget. And that effectively that might be configured as one of the collection parameters. And then from the user perspective, nothing really changes. You are still using the same vectors. You are inserting the same vectors and querying using the same vectors as you did before. But internally, we are just storing that differently while keeping the original vectors intact. So you can also like reverse that and decide to come back to the default precision. But you can also push the scalar optimization to the limits by binary quantization. This is a different approach. Instead of using integers, we are using Booleans that effectively reduces the memory requirements by up to 32 times. And this is a feature that was introduced in Qdrant 1.5. And not all the embedding models work properly with this kind of optimization. But if you are a happy user of OpenAI, Cohere AI, you can probably use this technique and reduce your memory requirements by up to 40 times. But that also comes with another advantage, because if we decide to use either integers or Booleans, our operations done on the vector levels are also way faster. And this is a simple comparison given the original querying time and querying speed actually, and the memory usage. With scalar quantization, we are able to improve the latency, reduce improve the speed by up to 4 times. But with binary quantization, even with up to 40 times. So this is way more effective, and the impact on the precision of that search is not that huge. With OpenAI embeddings, it's around 1%. So this is still acceptable, and you can always combine it with some rescoring after. So basically, you are able to fit 32 times more vectors on a single machine than you used to be, just by enabling a simple configuration option. So that might be done in that scenario. And if you have any struggles with implementing semantic search, I'm happy to answer some of your questions now, but we can also stay in touch. Here are my social channels that you can easily use to send me a message if you have any problems with Qdrant or vector search in general. And if you just want to experiment a little bit using our Qdrant cloud with a free tier mode, there is a 1 GB cluster available for everyone without credit card details, and this QR code points directly to our cloud offering, so you can start using it just within a few clicks. Thanks a lot. I'm looking forward to your questions.
Yeah, I don't know if they need the. Yeah, we can check the button. Yeah. Thanks, that was a great presentation. When you're using the binary quantization, what class of searches or documents or corpus of data is best suited to select that level of quantization?
I would say definitely if you work with some critical data, you cannot afford like reducing the search precision, but it's more about the embedding model. So the higher the original dimensionality of your model, the better it works combined with binary quantization, I would say. But it's not about like a specific data set. It's more about there is some redundancy in the higher dimensional vectors, and that might be sacrificed by reducing the precision of representation. And from our perspective, it's more about the embedding model than a specific data that might be like worth checking out. Maybe some specific scenario might work best with this kind of implementation. There is another question in the back.
I can just talk.
Okay.
We'll give you a mic. Yeah, okay. Well, great presentation. Thanks very much. My question is, curious whether you have any kind of scoring system, framework, or benchmarks that you use to measure how effective HNSW is relative to peers or internally when implemented versus not. What basically might we be giving up with that versus not, or if somebody was wanting to switch from something else to people?
Well, basically, this is not based on our like own measurements, but it's more about there are ANN benchmarks available out there, which is like this is a website that publishes some sort of comparison of different algorithms. I'm pretty sure that our core team has some sort of internal tools that they use to measure the performance and the quality of HNSW. I'm just not aware of them. I would need to ask them directly. So I'm sorry. Yeah, but I'm happy to like ask them directly and get back with an answer. This is a pretty interesting topic, actually.
Anyone else?
What's the typical total size of the data, and how much is it usually broken down? How many different documents?
Well, so there are different scenarios. Like, of course, we have lots of users using just the free tier to just do some experiments. So it's roughly less than a million of embeddings. So it's not about like documents. It's usually like we have a document that we split into chunks. So it's hard to say like how many documents. Still, like we are not checking the data of our users, so I cannot like answer what is like the average number of documents they have. But I would say there are lots of use cases in which people have like a few hundreds of millions of vectors stored within a single collection. So this is like a typical setup. But that really varies. We have like customers using billions of vectors effectively. So really depends on a specific industry, I would say.
One more question.
Thanks. Great presentation. I'm curious about quantization. So you said, for example, you could quantize like a float 32 down to a single 8-bit integer, let's say. I hadn't come across the binary quantization before. Do you also, in that case, quantize a single dimension float 32 down to a single bit? Or can you take 4 bits that are 4 separate dimensions? Does that make sense? Is that a useful kind of trade-off?
Yeah, actually, this is pretty straightforward. We are actually converting a single float into a single bit. And the algorithm is really, really simple. If it's just higher or equal to 0, this is 1. If it's lower than 0, this is 0. And that's basically it. Actually, this is very specific to a model, as I said, and that works pretty well with OpenAI embeddings, at least with some of them, but they just tend to be higher dimensional than the others, and doesn't work that well with some open source models like all mini LM v2, which is quite commonly used. This is one of the sentence transformers. So actually, we have no clue yet, like what causes that, but basically probably there is some sort of redundancy in those higher dimensional vectors. So it's really specific to the model, and surprisingly that works pretty good. I mean, like if you, let's say you are getting like 99 or 99% of your most relevant documents for a specific query, you may simply get like 97 or 98 with binary quantization enabled. So this is pretty decent result, given the advantages that you get just by using it. So I guess much.
Yeah. So you mentioned the word rescoring, but you didn't explain.
Yeah, thank you. So yeah, basically, even if you enable scalar or binary quantization, your original vectors are still like kept intact and they are just stored on disk. So if you enable well, actually, this is enabled by default, but let's say you expect to have like top 10 results for a specific query. So with binary quantization and rescoring, we are, let's say, prefetching 40 elements and then rescoring them using the original vectors. Because if you have binary vectors, you cannot effectively calculate the similarity, because this is just all about 0 and 1s. So that effectively limits the possibilities here, how we could calculate that. Actually, in order to properly calculate the distance to of the specific document to the query, we need to have the original vectors, and this is what rescoring is all about. But if we just prefetch more vectors, more documents than expected, we could easily select the best ones just by calculating the distance in that limited space. So instead of calculating the distance to all the documents, we are calculating it to this 40 prefetched ones and then selecting the 10 best ones. So this is pretty simple mechanism, but also gives us this advantage when it comes to search quality.
Thank you so much.
I have another question, if we have enough time.
It's a quick one. So you were saying that when you quantize, you store the original vectors, which makes sense. And then I wonder, for the quantization, do you do it like on the fly, or is it like you also store the quantized vectors?
Yeah, we store the quantized. It's the usual setup is like by default, all the vectors are in memory, so we have fast random access to all of them. But if you enable any of those quantization methods, the original vectors, the one represented with floats, will be stored on disk, so there is no memory overhead generated by this. And the quantized versions of vectors will be stored in memory. And this is when this improvement comes from. So instead of storing like floats, you are storing a different data type. And that's basically the...
Yes, but I was thinking, if you have a terabyte of vectors that you keep there for like months, so they will be on disk. You don't store also the quantized version, so you will complete it on the fly, or
no, actually you store the quantized version in memory. Well, probably it's also stored. It's also stored in the on disk. I mean, like, yeah, it's stored on disk as a part of the collection, but it's not that. It's just not used while searching. So of course, if you just restart the service, we are not recomputing the quantized vectors at all. That's a really good question. They are stored as a part of the data on disk. So there is, of course, some overhead on the disk requirements this time, but storage is quite cheap. So probably not that many people will be just worried about it.
Anyone else? Thank you. So you are using binary-based quantization, and then you are again using a normal vector to rank them. What about using logarithmic-based quantization so that you can have ranking?
Well, definitely it's not implemented. Maybe there are some scenarios in which that may pay off. Would be great to know like a specific scenario in which you would like use it, logarithm quantization. But would it like change the data type that you can use? Like
it will change. Like you won't be using just one bit, but it would be much more less than integer 8 or integer unsigned integer.
Well, definitely that's an idea that requires some experimentation. I'm not saying like I have no idea if that would be working fine. Probably in some cases that might be a good option, but yeah, we need to like experiment with that. Definitely, it's not implemented.
Thank you. Thank you so much, Kacper, for this presentation. Great company.
Thank you.
You have actually a good news. Pizza is here. So we're gonna take a 15 minutes break and come back. Thank you so much.
We're done with this presentation.
Thank you.
You're quite new to Twitter, aren't you? Just have 2 followers.
No, not really. I have like over a few hundred at least. I bought them. So I'm pretty sure there should be more. It's not me. That's a different person. I turned it off. I'm not sure if I.
No, you're good. Yeah, thanks for on the fly going into the recording, coming off mute. Appreciate that.
So, then I ask you the question, we are implementing machine.
RAG application. And Andreas is going to take us through that. Sorry. Got it. Okay.
Yeah,
Okay.
well, thanks, Christian, for the intro. We're going to go through this real quick because it's been mostly covered. What are large language models? The students saw that. I mean, statistical language models have been state of the art since the 80s. But these new generative models have become really well known. It's amazing what they can do also for search and retrieval, which has been our wheelhouse for a long time. So we're going to talk about that. So what they can do, they can predict the next token, and if you have enough training data, this looks like intelligence. I'm not going to go into whether it's intelligence or not, because that is not really interesting. The interesting part is that it's undeniable that they are super useful. They can do an amazing amount of different tasks that are undeniably useful. So that's the engineering view of it. So how do you use them? You use prompting, which is often defined as writing instructions for the language model. Of course, you could also say it's constructing. You can do it. Technically, I think you're not really writing instructions, right? You're finding a space in the embedding space and moving the model into that space to get the output that you want. So you can do prompting with random tokens, which are prompts that are learned and not written. It's gonna accomplish the same thing with something that doesn't look like instructions at all. That's so here is one of the problems that language models have if you try to use them correctly. This is GP treatment, right? And obviously this is unlimited knowledge. This was not an unexpected event. Everyone knows this was going to happen soon, but at the point of training, the model could not possibly know. So, and obviously training a new version of the model is enormously expensive. Fine-tuning model is also not cheap, and it's very hard. There's a very limited amount of people that know how to fine-tune models, and all of those people are better at working on other things than doing that in many cases for when it comes to RAG applications. So another typical problem with using large language models is private or personal data. This is something that we don't want anyone to know. And it's unclear to me whether ChatGPT knows it and doesn't want to say, or if it really doesn't know. Right? If it knew, good luck convincing OpenAI to retrain the model to remove your personal information, because that's probably not going to happen. They're doing it more and more often, but still, it's not exactly real-time updates. It's really hard. Well, in this case, there's another common problem is hallucinations. When you ask the model about Vespa line, and we're currently on Vespa 8, Vespa line is very far into the future and not planned. So it's it does really well. It tries. I can't provide you with specific details because it's not out yet. and then it's sort of makes something up. I mean, like this last line is all nonsense. Great Norwegian company, Qdrant, but they have no relation to us at all. So that's sort of thing you get, and you can put updated information about the world into the prompt of the model. But it's a pretty limited space. Like I know that 5 days ago, Google announced a new model that has 1 million tokens. And that sounds like a lot. And people are saying, oh, RAG is dead, 1 million tokens now. So a typical token is about 4 or 5 characters a word. So that means that it's around 4 megabytes. So maybe your organization has more than 4 megabytes of data. Sometimes they do. So I think it's going to be relevant for a little while yet. So this is the basic structure of RAG, which is retrieval augmented generation. And I think this is pretty common knowledge. This is a figure I stole without asking, so I hope that's all right. But I think it's really good. It sort of shows you the very typical use case of generative models combined with vector datasets. And there are a lot of people out there teaching you to make this. And honestly, it can be fitting. This can unlock enormous value. Doing this is a first very simple pattern, and there are already 100 to 200,000 startups doing this for different kinds of data in different fields, and it all has proper models actually creating great applications. But it's not the be all and all. So you can actually explain how first. So you take the query, like Kacper was saying, you produce an embedding for all, and then you retrieve without embedding from the vector database related content related to the query. So you retrieve updated information about the world and feed this into the language model together with the original query. And then you generate a response. And this is going to give you a lot better results than just asking in language model, right? Because you can update this content in the database, you can modify it. It's a lot cheaper, a lot faster. It makes a lot more sense than retraining or fine-tuning the model every time you have a new document. So now with this architecture, there's like a simple 4-step. You set up the vector database, you figure out how to turn the text into these things. You write some integration code and do it design, and then you're done, right? You have a RAG application. It's amazing. It's going to unlock tremendous business value. Except there might be a few things that you still have to do. First, you discover this. You need to gather all the relevant information you need and put it into the vector database. Because if you don't have that, then the RAG is not going to help you. You need the relevant information in the database. And you need to break it down into the sort of chunks that your embedding model can understand. You need to format it properly, parse tables from PDFs is a common issue that people spend months and months on. And then you make it further people overflow the complex window. And like I said, this is still quite possible. It's 4 megabytes. And that you just don't fill it up in duplicates of the same paragraph. Like if you're indexing email threads, and each email is going to have the same paragraph that the previous email in the thread had. And if that paragraph is determined to be very relevant, you're going to feed your language model maybe 10, 20, 100 copies of the same sentence. It's not really going to help in any. So these are the sort of challenges that you end up discovering. And here's the big secret is that you are now in a well-known business that you're doing information retrieval for search. And this is the same thing that people have been doing since this is a field that started in the 50s, right? It's a mature field of research. There's lots of known challenges. So the first one we talked about, the second one, especially adversarial data, is something that you're going to see in all cases. But if you're searching the web, you're going to find spam, you're going to find fake news, there's data quality issues. It's never going to be perfect in any case. And you still all have the challenges of a large language model, in addition to the challenges of information retrieval. And even if you have a lot of relevant content, you're still going to get hallucinations. So we way less, but they're still going to happen sometimes. So you can't guarantee it. So if you're working in a medical field or verify if possible. Really through a human if it's important. So in our case, it's not that important. But we can also realize that this is not only a problem. This is a mature field of research. There's lots of strategies that you can know. These are the most common methodologies for evaluating how relevant are the results that you are giving. Let's normalize, discount the gain, cumulative gain. That's next level. And 10 results, which say how many relevant results are in the top 10. And where are the most relevant results within that? They are scored. So you are having human judges judge the relevance of the documents producing. And the other one is the industry standard for most use cases, which is very soon to at a few topics. That's what most people do. But you're not at the starting line with information retrieval. You're doing analytics, then you keep ahead. You moved from the 50s, the 60s, lead forms right into the 2000s, 2010. So you're way ahead. You're not dealing with multiple language issues, stemming and misspelling. Sort of those things are handled by that trained language model for you. So it's a huge improvement. It's a great start. And there are more advanced methods you can use. Like compare, they're pretty close to current standard. And here's one that most people don't realize. But if you already have search, what you're doing with RAG is you're retrieving relevant information and placing it with the language model. And you can do that with your existing search. Even if it's a test search, right? It doesn't have to be accurate, it's still gonna find pretty relevant information and you can put that in language model. You don't have to build the whole vector thing first if you already have search. And we're actually going to get into later why this might actually be better. Because language models have really poor matching for exact identifiers, don't go well with embeddings, names, phone numbers, email addresses. For these sorts of things, the exact string matching is still a huge upgrade over embeddings. That's worth knowing. So Christian is going to come in, and we're very lucky to have Christian with us today. He worked on this R RAG application, which we built for documentation search for our team to help reduce the support load. So Christian.
Demo time. Demo time. All right, let's see if we can pull up something more interesting. Let's see. All right. Yeah, sorry. Now I look old. Sorry about the full screen. So this is something we did last summer. All our users complained because we had too much documentation, so it was not possible to find anything. So we had to build something better. So we built a RAG. Funny enough, yesterday we found a Vespa user that he had said exactly the same thing. So he also built a RAG. So that just proves the point that we had to do something. So this is something. Oh no, what happened here, Andreas? Okay. That's too fun. We have some, maybe we have exceeded our limit. Oh no, okay. All right. Oh no, Andreas, what's going on there? Too much traffic. We shouldn't have shown this to the Stanford guys. All right, let's skip to the.
Yeah.
Yeah.
Try it on your phone, guys.
Yeah. What's so much?
Nice.
Yeah. Let's see. Okay. So there are three things that let me just show this. And now the wrong window. Okay, let's do this. Let's do this. So there are three things you need to think about. What is that we are going to talk about. One is how we are providing the context that we feed into the large language model. Another thing is how you help the users do the right searches using a large language model. And finally, how we do the ranking. And this will be a bit more advanced than the previous talk. So apologize for that. We are using Vespa config files and Lingo, but it is general, so bear with us. So the first thing we realized is that we are writing documentation for the machine. The important user is the language model. We have to write something that's understandable for OpenAI. So that means that we have to fragment our documentations into useful nuggets of information that are good by themselves. Preserving format turned out to be very important too, to have the language model make sense of it. So this is what we did. We have a lot of documentation in Markdown and HTML and some other formats. So we have to rework that into useful fragments. Doing things like everything in between headers is a good fragment, turned out for us. Table rows are good fragments, particularly for reference documentation, and people look up that a lot. So in our old search, you hit the right document that was a 25-page document. So good luck finding what we were searching for. So creating good fragments is really important. Everything must be linkable. So either you have to auto-generate the ID or do it yourselves. And the better you're at this, the better the summaries will be in your search. So this is our prompt that we were using. It's quite easy or similar, simple. Some simple instructions. This is the context we are talking about. This is what you're pulling from your search engine. We provide it here. Often it's like the top 10 hits or the most relevant hits. And the user query is here. This is what we sent to OpenAI. We used the 3.5, didn't we?
I think we might have switched to 4.
Okay. So what we realized is that for our use case, that is technical documentation, is that OpenAI provided some really good results that were almost right all the time. The problem was the times they were wrong. So we found that we would center the results from OpenAI a bit, out of the center. We will focus on our own search results, have the language model provide the summary linking into our own results. So we put the focus on what we retrieve from our database. That was one thing we found. Another problem we were looking at is how do we guide the users to do the right queries. Again, the solution was quite simple because once we did all the hard work with fragmenting your documentation and creating really good pieces of information, you could just take that and put it to OpenAI and say, what's a good query for this piece of data? Or give me 5 queries. And they did. So, and the search suggestions are awesome. That worked really well. So I'm going to show you how we index that after. So that was easier than we thought once we did the hard work on the content. So this is what a fragment looks like. This is a piece from our reference documentation about some access logging. I think it's Markdown. We index it like this. This is a bit shortened. The thing in italics is much bigger. But you see here we index a combination of the content and what are the good queries. This is the output from the large language model, and this was done offline. So this is done before indexing, or you can just put it in the indexing pipeline. Whenever you change this document, we can just re-query. This is how you configure the data. It's part of it. It's not a complete configuration. So this is what makes this different from a pure vector search database. You see lots of things that looks more like a database, like a schema config here. So we have different types of fields like strings, could be integers, array strings. You can also find tensors here. So that is what Andreas said, that you're actually querying into more structured, and it could be unstructured data too in your RAG. So this is our schema. Kacper also mentioned embeddings. Sometimes you create them on the outside your system. In Vespa, you have the option of also doing it inside. So you can inline it into your indexing pipeline. So you essentially just send the text that I just showed you the markdown, the JSON that we feed into the system. So you can create embeddings on the fly. That really offloads or reduces the complexity of your system. So this is the fun part, or at least what I think is the fun part of the presentation. This is what we call a rank profile. This is how you decide. This is the secret sauce of your application. This is how you're ranking your data. So what you're looking for here is the semantic part of the rank profile. This is also what Kacper talked about, the vector similarity. This is the cosine distance between a query embedding and the embedding in the data. So this is part of a larger function that also has text scoring. So we have a combination of vector similarity and text signals. You could also have lots of other things in here, like filters and those things. So you decide how you score it. This is just math. So it's a kind of generic ranking engine. So with this, you can do both the vector similarity and what we normally do in your search application from before. So if you do this, then you will have a well-functioning RAG application. So this is also quite interesting. A tensor is kind of a multi-dimensional structure. It's like a vector is a one-dimensional tensor. Tensors are input and outputs from models. So it's very commonly used. You will find it a lot in the Vespa application, because people can also use models here. You can import an OnX model and feed a tensor into it and use that in the ranking as well. I didn't include it there for simplicity. So tensors is something you should look at. There are some links at the end there to our blog site that has some good examples. All right. Why doesn't it show?
Can I fix the full screen?
Yeah, please do.
Thanks. Okay, nice. Just now.
Yeah, if you stop the full screen.
I think this is worth doing because the text is pretty small on some of them.
Yeah.
Let's move this down. And then we do it again. The usual. There you go.
That's better. All right. Okay. So this is what failed earlier. This is the search suggestions. These are the things generated from the LLMs. This is the output from the ranking question I just showed you. So you see that it looks like a substring search, and it actually is, but it's a combination of similarity and text substrings. So this helps your users if you are able to do good suggestions. Let me just skip this. This just shows that you should also be able to add filtering, the green buttons. So this is a more complex example. This is not the suggestions, but the data itself. And it's just an example of a multi-vector search. So in this case, we are using two embeddings. The query on top of here is referenced in this expression. So we do a combination of semantic question and semantic, meaning two different vector distance calculations. So you're able to express this in the rank functions. So it can be quite complex. And this is the text matching part as well. So I included this just to show you that again, it's just math, and you can do this arbitrarily difficult if you want to, including model inference. You also see Kacper talked about types of data in your vectors. So this is also configurable here. It's floats, but you can do whatever Kacper just told you to reduce size. Okay, let me just skip that. Okay, I included this for Microsoft, so thank you for the 5 models. This is what we're using. Yeah, so I'm skipping to the end. Yes. So these are useful links. We'll be here after for questions. We really recommend our community Slack if you want to follow up. There are great blog posts that addresses what Kacper talked about, things like how do you optimize for memory and speed and those things. So you should go there. I think, yeah, and here's some contact info as well, in case you are not able to get us now. We are around in the area for a couple more days, so we're going back next week. So we're really interested in talking with users about use case. Any questions? Yes. Are you moderating? Yeah. Yeah.
Hi, a question around, you mentioned that you perform summarization after you receive the documents. Is there any way that you're evaluating the quality of the summarizations without human intervention?
Yeah, that's a great question. Because how can you do that? And it's like you can easily see that. Well, we asked the model to provide pointers into our documentation to know what are we talking about, because it's generated. So we haven't found a good metric or how to do that automatically. Andreas has a good metric. It looks good to me at the top. Yeah. Like
Industry standard.
yeah, it's very hard. So, but I know there has been a lot of talk lately about using guardrails and those kind of things to try to constrain the model from going totally haywire. So I don't know that that's answer.
Thank you. And just one more.
Yeah.
With the queries, you are currently using LLMs to generate those queries, right? But have you considered basic, like going back to the basics and doing something like query expansions or modifications, or that doesn't really about that?
You can do that too. I'm sorry the demo broke down, but we send the user query and the embedding from it. But we, as you type, we create those suggestions based on the pre-generated queries that we make offline. So you can choose not to use those and just send the query as is. So and then you can do all kinds of query expansions that we talked about. There are a lot of functions in us that do that.
Thank you.
Listen, thank you so much for the presentation. I would like to know, how did you find out all this like weights and formulas for your fun part with email?
Like this. We are only 30 people, we need more people. So of course we should have done relevancy experiments to feel that better. So maybe our some interest to do that. I don't know. So it's it needs more work, yes. So they are wrapped up. So there's like a thumbs up and down in the result, which you can use to give feedback. That's the sort of thing that you really want to do. If you have a large product, is you want to
collect that user feedback and use that to fine tune, instead of having to hire people to judge the relevancy of the search result you can see. Whether the user likes it or not, or you can do what is on. Sometimes in web search, you can see that if the user clicks the first link and then doesn't come back, it was probably the right one. If he comes back to the page and goes to link 3, let's make it link 3 better. That data is to feedback and fine tune one another way to know.
They've obviously got that small metrics to measurement. Great questions. Any more? Okay, excellent. Thank you.
Thank you. Thank you. Thank you.
Great presentation.
And thanks to you guys, AI Camp, for hosting us. Hopefully not last time.
Yeah.
It's our first time.
Yeah, welcome back. Absolutely.
Thank
Yeah.
you.
Now, I do want to say before, of course, you're free to stay and network and continue to talk to the presenters that have obviously just bestowed a lot of good information. We do have a raffle, right? So for those at the start of the presentation that I had at the beginning, there was some QR codes and a bunch of people took pictures of those QR codes